Hello, everyone. Welcome to my channel. And today we have with us Apoorv Pochiraju, who is a ML researcher and scientist at Lawrence Livermore National Lab. So let's find out what Apoorv has to share with us. Hey, Apoorv,
Hey,
welcome.
thank you for having me.
Yeah, Apoorv, can you share? Can you tell us about your journey from being an undergraduate data science student to becoming a machine learning researcher at Lawrence Livermore Lab?
Sure. I'll start off sort of, the journey kind of starts in my freshman year of college. That's when, I became a data science major. And so as a major, it's pretty broad. There's a lot of overlap with, computer science. So I was kind of unsure on which track to really go, considering data science is, pretty broad and you have different avenues that you can, really go down. But, it starts off with getting like a good fundamental, background in like software engineering. And then from there, you sort of once that background is developed, you learn about statistical methods and then combine both and then figure out how to solve problems with data. So at the time I was sort of confused. I thought, okay, maybe I'll just become like a data scientist in tech, or I'm unsure about which industry to sort of go into with this background. And so as the academic career sort of progressed, my first internship was at Pacific Gas and Electric, where I was a data science intern, and it's a utilities company. So you're working with utilities data and grid data, especially from grid sensors. And there's a lot of optimization problems to be solved there, and a lot of forecasting problems as well. And so it was like a niche area in which I was applying my data science background in, and applying my machine learning background in as well. And I never expected to really transcend beyond that. I thought like, okay, because data science is broad, just this experience in in this field can sort of translate, and I can lateral into like any other field, whether it's tech or another industry. And I never expected for me to even obtain any other opportunities to pursue somewhere else in another field, right? Like in terms of applying data science. But I've still actually found an area to do research in. So in this niche area in Lawrence Livermore National Lab, because a lot of research opportunities and early stage research, people are working on a lot of these really niche areas, which usually don't get funded in the private sector, and frankly people don't really work on because they don't might not even see the potential. So but those opportunities do receive funding at a national lab or in a federal lab or an academic setting. So they were looking for, so when I applied to the lab, they actually were looking for someone who had a hybrid background of power systems and machine learning, and sort of fit the bill because of my background and the work that they wanted to do in terms of forecasting and optimization, especially working with utilities data and being able to come up with algorithms to solve these problems was something I'd basically done at PG&E. And so because the background aligned, they brought me on, and I was able to sort of continue the same track that I'd started when I was at PG&E.
So that's nice. So power systems and DER optimizations, they sound like complex fields. Could you explain these concepts in simpler terms for our audience?
Sure. So I'm sure you all know about the electricity grid. You have the power plant where electricity is generated, and then it comes to your home or your business, right? But now that itself is very simplified because you don't know what goes on, the intermediary areas between the power plant and the distribution grid where power is actually received by you. But the grid is very complicated. It's a very complicated network, right? And spans thousands or hundreds of thousands of miles, depending on the state and the region in which you live. And so there's a lot of maintenance that goes into it. There's a lot of operations, and a lot of labor is needed as well. And a lot of expensive infrastructure is needed for the efficient flow of power from power generation to when you receive the power. And so I'll just give like a simple overview of basically some terms and of how the grid works. So I mentioned generation. That's the power plant where power is created. Now typically it's a generation power plant using fossil fuels, and then from generating plant, power is sent through the power lines to you. But then there's also the transmission grid, which is basically high voltage power is sent from the grid across remote areas, hundreds of thousands of miles, because this is very high voltage power that shouldn't be around people, and it needs to go over those overhead lines. And once it reaches, sort of more urbanized areas, then it goes through a distribution grid, which is essentially like, another, it's a smaller network, but it's a more complicated network because now the power has to basically branch off to different homes, businesses, people, and areas efficiently. And so at that point, the voltage has to, step down, and the current that you receive is much, much less than what is generated, because otherwise, it would be incompatible with, your house, and you don't want such high current flowing through, your power lines. Otherwise, it's going to explode. So those are basically the key components of the entire grid. And DER optimization basically involves interconnecting renewable sources. So what I just mentioned is like the typical structure of a power grid, where the power generation itself is centralized, right? So you have generation plants that are somewhere out there in a remote area, and it's up to the utilities to basically generate that power and send it across the power lines to you. So you don't really control, the generation of power, right? But now what DER stands for is distributed energy resources, and those are basically sources of power that are decentralized. So if you have a solar panel on your house, that's a form of a decentralized power source, because now you're not relying on a utilities company and a power generating plant. You have a solar panel on your roof, which can generate power for you. Similarly, there's, like some electric cars that have batteries that can send power back to the grid. Now that can also be considered, a DER. So for people that do have these, right, they're generating power, they become their own little power producers. They can also send power back to the grid, right? And they can generate power for themselves. But also there's, they're using intermittent sources, which are basically vulnerable to changes in weather and so forth. And so with the expansion of these, now it adds, new complexity to the grid as well. And you have to manage, the flow of power depending on, the weather. And if there's surplus power that people produce there, then you can send it back across the grid to areas which need it. But if they're unable to produce it on their own, then they need to draw power from the grid. So it adds new dynamics in terms of like balancing load and generation.
Okay, thank you for sharing that information. So let's talk about your internship at PG&E. During your time as a data science intern at PG&E, what were some of the key insights or experience that influenced your approach to your current research in power systems?
Yeah, so I think when I started as an intern at PG&E, I was new to the entire area of power systems. Obviously, I obviously had the data science skills, that I could apply. I had knowledge of machine learning models and algorithms and so forth, but it's no good without understanding really well how exactly to apply them and where, right? When you take those skills and bring them to a new field. And so I think what really shaped my approach in my current role is the ability to just learn things quickly within the industry, because I was sort of forced to, right? When you're working with new data, especially from, in this case it was sensor data from the grid, or data from renewables generation and so forth, that from the service territory, and I don't understand what it means, right? And so first understanding exactly what the data means, analyzing trends within the data, and exactly how to leverage it, right? So because that's an open question. You might know what to do with it if there's like an actual question to answer, but like what happens when you don't even know what the question is? You sort of have to formulate that yourself. So that was a key component, and I think that initial stage of like formulating that research question and asking like how exactly can we leverage this data, and then get from there to the end point, which is like actually being able to, let's say, apply a model and put it into practice where like it actually serves a benefit, right? I mean, you can develop a model and have like a prototype, but the end goal is ultimately be able to use it, right? So take it from the research stage to actual like production stage, where it's actually saving utilities money or saving the business money, um, and being able to perform accurately in the real world. And so when you add that like initial stage, I think it becomes harder, but you also understand sort of the fundamentals of the industry itself and the complexities, and like exactly whether things will work or not. And I think that was really critical.
Okay, so you spoke about the issues regarding renewable energy and connection to the grid. So can you explain in further detail some of the pressing challenges and opportunities in the field of power systems, especially in the context of renewable energy integration and grid resilience? A little more in detail.
Yeah. So essentially the challenges surrounding at least renewable energy, um I could probably split the answer into two pieces. So one is, like I mentioned, decentralized sources coming in, right? So especially when you have solar, now people become their own power producers, so that adds new dynamics to the grid in terms of people can draw power from, but people now will still have to draw power from the grid, obviously, because when the weather changes and there's not enough sunlight, then they still need to power their home, but they can also transmit power to the grid. And so when you have that surplus power, how will you distribute it across a distribution grid, right? And so one thing is, as solar sort of proliferates at the consumer level, where people have their own solar panels, then that will actually sort of mitigate the need for more expensive transmission lines, which is a good thing, right? So you don't need a lot of expensive infrastructure on the transmission side, because that's sort of diminishing the demand for these power generating stations. But now the problem becomes, how exactly do you optimally distribute it amongst the distribution grid, right? Amongst an urban area, let's say, where people have solar panels and can actually they have a surplus amount of power to give to others. The second part is sort of integrating different sources, right? So people might have solar on the rooftop, but you can also have, a utility scale solar plant somewhere, right? Those are two relatively, I mean, it's the same type of renewable energy, but in terms of, like, the structure of how they work, it's relatively the same. Just like you interconnect someone's solar to the grid, if you have a solar plant, you would just interconnect it to the grid, and then you'd be able to basically distribute power. But then when you have, let's say, like a wind energy plant, that's a different type of renewable energy source, which is subject to different types of weather and whatnot. But you have to balance all of these, right, at the same time, to ensure load and generation are balanced. But then it adds more complexity to the sort of overall prediction problem, right? If you're trying to forecast and say, like, okay, how much do we expect, how much do we expect from this particular territory, and is the load going to be satisfied? How can we minimize costs when it comes to power generation? Are we going to have to basically bring out another traditional power generator? We're using fossil fuels because we need backup power, right? And that's the main second challenge. And I'll add a third component as well, which is now the energy storage, because as renewable energy grows, you're going to need to store all this energy somewhere, right? Especially because weather is volatile. So you don't have sun all the time, you might not have wind all the time, but with good energy storage technology that's more advanced, you might be able to build an energy storage plant and store it there. But then you also have to get it from there to back to the grid, right? So when you have to draw energy from storage plant or battery back to the distribution grid, now that adds more complexity. So it's these three aspects that you have to all balance, and they kind of upend the traditional structure of the grid. And so when you have these other dynamic variables along with it, it can become harder to forecast load and generation.
Thank you for sharing. So let's talk about some real world applications that your projects, where your research has had a positive impact on energy efficiency and reliability.
Mhm. Sure. So I'll give an example of the very first, actually, research project I worked on when I joined LNL, which wasn't actually related to renewable energy, but it was actually related to sort of like fault detection and maintenance in the power grid. So, just I'll give an overview of what fault detection is for the audience who probably doesn't know. But in power grid operations, power lines are vulnerable to maintenance issues, particularly when you have over voltage or overcurrent, which is pretty normal, or subject to just any other environmental conditions. It can even be wind or a tree falling on a power line. You would have a fault that occurs on that power line, right? And a potential fault can be really bad for everyone, because first of all, it causes an outage, but it also can damage the lines itself. And so then you need a maintenance crew to go in. And so it's a very expensive affair, and both the utilities and the customers both lose out. Now, mitigating faults is not relatively difficult now, depending on the type of fault. So a lot of utilities, what they do in the grid infrastructure is put like, protective relays or other protective devices that can sort of just like, trip when a fault is likely to occur based on, certain predetermined variables. And so you don't need any complicated algorithms there, but certain types of faults, specifically arc faults, which is what my research was about. Arc faults are, a certain type of fault which are very hard to detect because of their nature. So it's kind of like you can call it like an intermittent fault where or like a latent fault where they lay low initially. You don't see any like, blatant signs such as like a sign of spiking current or sagging voltage or vice versa. You don't see any outright signs when you look at like a sort of time series graph of the current being transmitted. And so it's very hard to detect. And then all of a sudden, it leads to a burst in current later on, like probably a few seconds after the fault is initiated, and then the damage occurs, and it can be very costly. So there's been a lot of research done to try and mitigate these faults, to try and develop some sort of models to at least detect the bad ones or the most expensive ones at least partially, so that they can use protected devices to trip to use the circuit breakers and trip the entire line earlier on, and ensure that no damage occurs to the line, and also power is still efficiently flowing. So I worked on building some algorithms involving signal processing and along with some machine learning methods, and because getting data itself was also an issue, worked on also like sort of data augmentation, synthetic data. So there's a couple of different components here, but ultimately it was a combination of signal processing and deep learning model that could actually detect arcing faults in the distribution systems to a certain degree, probably about 60% accuracy. But that was a huge deal, because as long as you can target the most expensive ones and the most damaging ones, and you have, let's say, a hit rate of 60% where you're able to trip early and avoid damage, that's a huge deal. That you can cut down on a lot of unnecessary costs and unwanted faults.
Okay, that's great. So how do you see the role of data science and machine learning evolving in the energy sector in the coming years? What trends or developments are you particularly excited about?
Yeah, I think so. Two main trends that I think will take off, and that I'm personally also eager to see happen, is number one, I think better forecasting models and a better infrastructure for it as well will also grow along with sort of like modernizing the grid. So as we sort of modernize the grid to include not only new renewable energy sources and whatnot, but we also upgrade the rest of the infrastructure. I think one thing that is going to happen is also simultaneously an upgrade of like sensors and SCADA systems, which are basically the systems that link sensors on the grid to sort of like the whole technology apparatus that the utilities have, so they can sort of in real time see any issues going on, and they can operate and monitor the status of the grid. But that involves a lot of technology. That's more on like the software engineering side combined with the data engineering and all that. So an upgrade of that whole tech, aspect of all these aspects of technology across the grid will enable, I think, better algorithm development, where sensors will be able to also be used to deploy these algorithms in the grid, right? So like there might be certain, like whether it's fault detection algorithms, forecasting algorithms, any other algorithms used for maintenance that are just sort of in-house. So, and they're more reactive, where if any issues happen in the grid or they see data coming in, then they'll sort of just use their internal systems, look at the data and say, okay, we run this model and this is what needs to be done. But when you have more real-time detection systems that can be sort of used on the grid, then you can really harness those algorithms in a much more efficient format. And I think that'll be more powerful, and that sort of goes along with this whole notion of like the smart grid. So where you have all these sensors, so specialized sensors and sensors that can actually record data in a more granular way. So, obviously, like if you can record current and voltage at a sub-second level and millisecond level, and then even further, like that technology is getting better and better as well. Um, and then the second part, I think, is like sort of an extension of smart grid, but as renewable sources grow from energy storage to solar to wind and whatnot, I think like when you have smart grid technology that can sort of better predict like load and generation specific to each source, specific to each service territory, and that'll grow as data sort of increases, because right now renewable energy is just growing, and so like when it becomes a majority of the power sources that we use, and we'll have better data in terms of like how exactly yeah, how reliable it is, and how exactly it's meeting load and generation needs, then models will also simultaneously get better, right? As amount of data grows, models can also get better. So I think it'll go hand in hand with better forecasting technology as well. And as well as if people install more solar, then you also have a better way of tracking what people's individualized energy needs are. So that's also one area where we don't have that yet, right? That technology is also getting better at the consumer level.
Okay, that's great. So, can you tell us something about how a typical week looks like for you as a ML researcher?
Sure. So a typical week is sort of it revolves around basically what projects you're working on, and how your team is also structured and your role on that team. So if you're like a primary researcher on the team, then your week is basically consumed with like reading research papers, or even writing research if you're in that later stage where you're trying to publish something, or whether you're trying to just get some ideas out there and get some feedback, or even presenting to other people who you may want some feedback on, right? Whether it's a technical audience, non-technical audience, or you're just trying to get out to a conference. um, so yeah, a lot of just sort of reading research papers, or reading up on some esoteric concepts that like you think are necessary to know about in order to inform you better about the research problem. Because a lot of researchers, like when they work on a new project, like don't assume that they know everything about the problem. They might have a certain skill set, but they also have to be able to apply it to a larger problem, or even if they're working in an area which they might not have experience before. For example, I work with people who are very skilled on the machine learning side. They're very talented machine learning researchers, but they know nothing about power systems. But it's a matter of just reading, picking it up, and understanding the complexities of the data and so forth. And there might be a specific um, sort of role within the team where like they don't need strong power systems knowledge, but we can really leverage their knowledge of particular machine learning algorithm or so forth, and their prior work. And so a lot of like I said, reading research papers, and then also if you're in charge of putting that into practice and in charge of the trial and error, then depending on what your research project entails, then you'll be really hammering out whether it's the code to put that into practice, or whether it's like the proposal that you're talking about, whether it's the ideas that you want to try. And so that's what your entire week is basically consumed with. If you're sort of the team lead on a research project, then I think it's more delegation. So you really try to just push people to sort of get it done, and you're in charge of like the overall direction. So if you have like a particular idea, then you look at the prior work and see like, okay, like what can we do differently that constitutes some sort of like innovation, and say, okay, like it's not innovative unless we try something different, whether it's a different model, a different approach than what the prior work entails. So like, let's look into that. And then, depending on how feasible it is, setting the appropriate deadlines and so forth. And so I would say that as an ML researcher, like on a team, there's, you need two different types of people. I think there's one person that's sort of like the more academic oriented, where they really understand like the theoretical aspects of like, being able to read the papers and then like translate those into like real decisions or like real ideas that you can pursue, and then the person that's like able to put into practice, right? So like one person that understands like, okay, how can we quickly like work with data, whether it's like building a library that can like do this, and then seeing the results, and then taking care of the entire like design phase, development phase, and so forth. And other people on the team can fit into one of these two buckets, and like work for these two people. So I think it'll depend on the structure of the team overall in terms of like what your week looks like, and there can be crossover between these two different types of people, but that's generally what it looks like.
Okay, thank you. So let's talk about advice. So there are many people who want to become data scientists and come to different applications of data science. So do you have what will be your advice for such aspirants who are interested in pursuing a career in power systems or related fields? Or are there any specific skills or knowledge areas they should focus on?
Yeah, so I think for anyone aspiring to go into data science, the one good thing is, data science itself is actually a very, very broad field, right? I think data science is just a set of skills that basically just involves a hybrid of, let's say, computer science fundamentals plus statistics plus just like mathematical reasoning ability. But you can take those skills to basically any industry, right? Like it's different from being a software engineer where, your role is specifically to just build software applications. And even though you can take that to any industry, really, tech is really where your potential is best reached, but also where much of the work really happens, right? But like in data science, there's problems to solve in any industry, and ultimately data science is just leveraging data in order to solve those problems and for decision making, right? So wherever there's a lot of data that can be used, right, you can find a way to somehow leverage that and essentially, solve a problem that hasn't been solved before, or find a better way of doing something and improve a decision making process. So I think in terms of like, an academic career, to start off with, like, learn the computer science fundamentals, like, learn, so like get good at that mathematical reasoning ability, because that is what will sort of like scale for you, right? It's not just about learning about a specific model that you can use, or learning about one specific method and whatnot. It's more about that broader sort of cohesive picture of like, okay, when I look at data, when I look at a problem, can I sort of deduce like, okay, like what makes sense? How do I go about pursuing it? And how do I go about communicating, my insights to other people who may not have a data science background? So I think that is what you should focus on. And then, once you have that sort of base and that foundation, then you can take those skills to any industry, and you can think about like, okay, you know, is there any specific industry that I want to, work in and I can bring my data science skills to, right? I mean, there's always the tech industry, but I think in a way, being a data scientist in the tech industry is sort of the same as being a data scientist in another industry, whether it's like the medical industry, let's say like healthcare or energy, or, any industry that has data, right? You're simply just working with, teams and that just have a lot of data and are trying to figure out what to do with it. Um, and so I think once you have that base and you can figure out, okay, like, which industry do I sort of want to take these skills to? And if, on the power systems side that you were mentioning, I think, a lot of that, like a lot of work in that field relating to data science is still sort of, developing and growing. And so I feel like a lot of people that are involved in that field are either in sort of like the research end of that, or if they're working for like a startup, or you're at a utilities company, right? But I think it's going to grow more, within the next couple of years, or like in the near future. So I think even if you get started sort of in a research phase, or like in a research setting, it's not a bad idea, because then I think, as like I said, as technology grows, data grows, and renewable energy also grows, and the field expands just the same way other industries like the tech industry, expand. Then there'll be a way to apply those, apply that work from the research setting and take it to an industrial setting. So
Okay, thank you. So let's talk about collaboration in research. So as we know, collaboration plays a significant role in scientific research. Can you share some experiences where collaboration with other experts or institution has been instrumental in advancing your research objectives?
yeah, I think this kind of goes back to what I was saying about the team structure of, on a research team, and like how that informs like, your role, and sort of how your day to day is structured. But I think, I'll add one other point to that is, yeah, I think getting third-party feedback or like consulting with other experts can also be, huge, because obviously you will come across like sub problems as you solve your problem where you might not know, what to do. It's kind of like a fork in a road, or, just an area which, is you don't know about basically. But in order to optimize on like, time, in order to optimize on sort of finding the right sources of knowledge, it's best to consult with these people, because I believe that, like, in order to, basically learn about something, it's better to go as close to the source as possible. Like, you can find information online, it might be generalized though, but sometimes you need like the right knowledge for at the right time for your for the right sub problem, if that makes sense. So um as in my experience, while working on a research team, as people on the team, just from their day to day, as new problems come up where, okay, they might find like, one small problem relating to, let's say, machine learning methods, right? And even if they do have a proper machine learning background, it's something that they don't know about, but information about it might be hard to find, or might be critical, or they want to ensure that they have the right approach here. You might bring in, someone with a machine learning background relating to that specific problem, who's actually worked on solving that before. And that's usually like the best source to go to, because first of all, they've kind of been there and done that. But they have that specialized knowledge for that specific sub problem, that and they can guide you through it, and let you know whether your approach is right or not. Because, and it also saves you a lot of time, because instead of you going through, let's say, other research papers to try and find information about it, or going through the internet to try and find information about it, or any other sources, they can exactly tell you what to do in many ways, right? So don't underestimate the power of actually, like, people and experts who have worked on that to actually help you, right? They all amplify sort of your productivity when it comes to research, so you can actually just focus on your output and your deliverable. um, right? So I think collaboration in terms of having a diverse skill set within your own team, right, where it's properly structured so that everyone has their own responsibilities as playing to their own strengths, but like also when you encounter any obstacles, you can consult with a third party expert who's sort of solved similar problem before and can help you.
Okay, so let's talk about something about your personal life. So, beyond your work in power systems and data science, do you have any personal projects or hobbies that you are passionate about and would like to share with our audience?
Sure. So, outside of the whole core, career academic realm, I think I like to play tennis, for fun on the weekends. I started playing when I was in high school. Oh, actually, before that, when I was like 13 or 14, and I played in high school. And now, even though I play less than I used to back then it was very frequent, like, a couple times a week. But I try to at least play, either on the weekends or, every other week. And so, I have a little group that I play with. So, it keeps me active, which is good. Other than that, I usually just like going to the gym, or working out, if I'm not playing tennis.
Minute. Okay, great. So, how do you stay updated with the latest developments happening in your field?
Yeah, so the best way to stay updated, I think, is either just keep reading, and keep talking to people. And when I say keep reading, that can mean um, whether it's research papers within your research area, or whether it's just more general reading, like online, about new developments. For example, if you're like an ML researcher, and there's a lot of new advancements happening, right, with like LLMs and all these chatbots. So if you don't work in that field, or you work in something related and you want to know, yeah, about that and keep yourself updated, then you can go on Medium and read articles. And the level of detail in which you read can depend on how much information you want, or how much information you need, depending on what you're working on. So reading is the best way, and especially if you already have, I think, a background in a certain research area, then I think by design, you probably already are used to sort of like reading academic work, and like reading detailed like research papers in the nature of your job. So you get used to it after a certain point, which is a good thing. And I think people who work in research do like reading to a certain extent, or they grow to like it because they have to keep doing it. So I think, just continuing to do that, and even on new topics is very helpful, because, details are always the best way to learn about, something new, if you really want to gain knowledge, and specialized knowledge. And then, of course, talking to people. So, there's people out there who solve problems that, you haven't solved, or like whatever you want to know about, there's always someone who's probably already working on it or done it. And so making connections, whether it's in the research world or whether in the corporate world, or just with somebody, you can even be a PhD student working on something that, you want to know more about, and they'll probably give you a better explanation than many people in the corporate world, because they actually understand like the fundamentals, right? So I think that's the best way, just, reading literature and people.
Okay. So, what are your future goals and aspiration in your career as a ML researcher? Are there any upcoming projects or initiatives you are excited to be part of?
Yeah, so in the immediate future, and in my current role currently, I'm working on projects actually for like DER optimization, like I mentioned earlier, but connecting renewable energy sources to the grid in an optimal form. So that means sort of like the grid is a huge optimization problem, and so like algorithms to try and simulate scenarios where with scenarios where you have to balance both grid and generation when new sources are connected to the grid, and also when you have decentralized sources. And our current work is sort of like aggregating different data sets and like working with different utilities to be able to access data and do this, and only then can we actually like put it into practice. And so it's a lot of work will go into it, but it's pretty exciting, because we'll actually get to try it, and the utilities are also excited to be able to hopefully use some of these models and then see how they perform. And we're working with them in conjunction, right? Because we're in the early stages of it. But beyond that, I think looking at my longer term career, I want to be able to obviously pursue this hybrid area of ML and power systems. I think as the area grows, I'll be able to also shape kind of where I take my current work and skills. I mean, obviously, I can go work at a utilities company um, and do this, but I've kind of done that, and I think the future of the field is more exciting. So, we'll see. I do enjoy working in research, so I hope to be sort of in an R&D role in the future, right, where I get to sort of combine these two areas, or even if it's more power systems focused or more ML focused, it doesn't really matter. It's ultimately just solving problems within the area, and so hopefully some sort of R&D role within this field that's cutting edge.
Thank you so much, Apoorv. It was a pleasure talking to you, and the knowledge you shared was really amazing. I knew a little bit about power systems, but not this much in detail regarding optimization and fault control. So thank you so much, and I'm sure all our audience will be appreciating the knowledge they have gained. And thank you once again for being part of the show.
Sure, yeah. Thanks so much for having me. It was a pleasure.